This will be the last example I'll be solving from metric. So we have the Euclidean plane for R2. So we have this function. So we want to check if this function is a metric. So we have this, and this is the same thing as this. You can actually use this approach for the question where I is from 1 to n. So remember, each xy is in R2, so that shows they have two components each. So that is what R2 means. So they have two components. So we have to, when we are talking about x, you are not just using x, you are using x1 and x2. So that shows this function is from what? Is from R2, Cartesian product of R2, which goes to R, right? It goes to R. This and these will actually be in R. All right. So remember, the first thing is to what? Is to show that 0 is less or equal to the xy, which is less than infinity, right? So we know that our dxy is this, right? Now we have x and y to be in R2, right? So each component, right, xi minus yi will actually be in R, right? That is, or let's say x minus y. X minus y will be in R, which is what? So I will say from I equals 1 to 2. So that shows x1 minus y1 and what? X2 minus y2 are in real, right? So each of these, when you subtract, right, x1 minus y1 is in real. Remember, each x1, x2, y1, y2, they're in real. Each one are in real, but x is in R2. So that's what we should know. So that shows the subtraction is actually in real. So then when we square these, remember, each of these are in real. Each of them are in real. So when you square this, xi minus yi squared will also be in real, because xi and y are finite numbers, they are not infinity. So when you square them, they will also be a real number. Then that shows square of each of these will be in real. Then you find what? The summation of these numbers, that is, you add these two numbers together, I from 1 to 2. And if it is from 1 to n, the same way, just that you sum these n times, but these are just two components. So you sum these two numbers together. Two real numbers, when you sum them together, will also be a real number. Then you find the square root of the sum. Remember, anything you square now, let me say that, square now will be what? Will be greater or equal to 0. Xi minus yy squared is greater or equal to 0. It can be 0 when x is equal to y, and it can never be negative because of the square. When x is not equal to y, it can never be negative. So we have this to be greater or equal to 0. Then if you sum them, I equals 1 to 2. If you sum them, squares, two numbers that you squared, when you sum them, if it is 0, then it will still be 0. If each numbers are greater than 0 and you add the two together, they will also be greater than 0. That is what this means. Then you find the square root of those numbers. Which is same thing as the 1 over 2 on top, right? So if you find the square root of 0, it will be 0. Or if it is a positive number, it will also be greater than 0. Because it is not a negative number, then the square root will also be greater than 0. Then at the same time, remember I said earlier x and y are less than infinity, so the subtraction will be less than infinity, the square will be less than infinity, then the sum will also be less than infinity. So we have 0 less or equal to this, which is our what? dxy, which will be less than infinity. So we've done the first one. Now the second axiom says, when would this be equal to 0? So this can be equal to 0, remember, equals 0 if and only if x equals y. So two sides, right? So the first side, so if, which is this, dxy equals 0, what's the definition for dxy? It's saying square root of sum from 1 to 2 of xi minus yi squared is equal to 0. Square both sides. When you square both sides, you have square both sides. So we have sum xi minus yi squared will actually be 0. When you square 0, you have 0. When can the sum, remember I is from 1 to 2. So when can the sum of this, you can actually write it this way, x1 minus y1 squared plus x2 minus y2 squared. When can this be actually 0? That is when each of these are 0. Both of these must be 0 to have 0 as the output. So if this is actually 0, when can this be 0? Because this is squared. So square will always give you a non-negative number. But when can it be 0? Remember this, each of these is 0. So when can each of these be 0? That would be when x1 equals y1. And this also will be when x2 equals y2. So if x1, x2 is equal to y1, y2, x1 is equal to y1, x2 is equal to y2. So this is x, this is y. So that implies that x is equal to y. So which is the same way when you do it here. When x is equal to y, you write it this way. So I can actually do it like this. Like it gives the same thing if and only if and only if. So this will be if and only if. So you start from here. When x is equal to y, you write the same thing. Then we get here, that shows x1 is equal to y1, x is equal to y2. Then you get here, you get 0 till you get to the top. So that is actually the second axiom. Then the third axiom says the xy is actually the distance from y to x. Once again, what is our distance from x to y? Which is this, right? Then you have your square root. Remember these, you can write this way because of this square, right? Okay, let's rewrite this. This is something as negative yi minus xi. We are still writing the same thing, or 1 over 2. So this is same thing as this. But remember, you have a square here. So when you square this expression, negative 1 squared, this is just like ab squared, which is a squared b squared. So negative 1 squared is 1. Then yi minus xi squared remains. So we have sum I equals 1 to 2 yi negative xi squared 1 over 2, which is something as what dyx. So we can see that it satisfies that condition, symmetry. So now the fourth condition, that is triangle inequality. So xy is from the distance this plus distance this. Once again, what is our dxy? Which is xi minus y squared I equals 1 to 2, 1 over 2. Now remember, you can rewrite xi minus yi this way, which is xi minus zi plus zi plus yi. Remember, for all z, which is z1, z2, which is also in R2. So for all z in R2, so z also has 2 components. Alright, so we have this. So let's substitute this in our expression. So we have I equals 1 to 2 xi minus zi plus zi plus yi all squared, right? All squared. So I can have this, I can put it this way, everything half. All right, so we want to break this down, right? We know that this will be less or equal to some expression, but yeah, because of this course, so let us introduce this. This is the statement for Minkowski's inequality. So we have this. So we have our p needs to be between, yeah, it can be equal to 1 or greater than 1, then it will be less than infinity. So, and in our case, p is equal to 2. Then we have ai, bi, which is our x, y, yi, zi. So in our case, I is from 1 to 2. Remember our expression here. So this is like our, oh sorry, so this should be x and y. So I can use this to be AB, then this will be AB, A and B. So, and this will be my A, this will be my B, AI, BI. So that shows this expression is less or equal, that expression is less or equal the sum from 1 to 2 of xi minus, so what's the first one? Minus zi squared 1 over 2 plus applying Minkowski zi, sorry, this should be negative, so this should be negative, so zi, it doesn't matter whether it's okay, that's fine. All right, so we have this which satisfies our triangle inequality. All right, so let's move to another thing on metric and topology. See you in the next video. Thank you.